Logism allows you to design and simulate digital circuits. It is intended as an educational tool to help you learn about how circuit works. In this video, I am going to explain a simple way to practice using logism for beginners. This is the main window of logism. This hand symbol represents simulation cursor. I will talk more about it later. The arrow is a regular arrow. It is used to connect gates. A here is a text box. It is used to insert text part for the circuit. This is an input. This is an output. This is a NOT gate. This is an AND gate, and this is an OR gate. This part of the screen represents more libraries and more gates that we are not going to use right away. Let's build simple circuit of AND gate to understand how to use this logism. This is the truth table for AND gate. There are two inputs A and B. So we take two inputs A and B and X is the output here. These are the inputs and these are the outputs. Here the two inputs are A and B, and we can place our inputs here. These are the properties of input A and B. These two are the inputs. Let's label them. To label them, I click on the button A and bring it before this input and name the inputs. I name the inputs as A and B here. I also need one output, so I click on the output button. This is the properties of output. In the properties of output, here the facing property shows the direction of which the output face. Here it denotes west direction. This is the properties of input. Here the facing direction of input is east. Then we move into the example. In here we need an AND gate. So we click on the AND gate button and place it here. Here output should be an answer from AND gate. To connect the output with the AND gate, we should left click on the terminal of AND gate and connect with the output. Then we again left click on the terminal of input A and bring it to the AND gate. And also left click on the input B and connect with the AND gate. Here we have only two inputs, so the number of inputs should be changed to 2. Now it's time to simulate. To simulate, we use hand button called simulator cursor. Here I can change the input to 0 or 1 by clicking on the input. Now Let's look at our truth table. Here A, B are the input and X is the output. Here for the inputs A to be 0 and B to be 0, the output X should be 0. So it works here. Here when the input A is 0 and B is 1, here the output X should be 0. So it works here. In here the output A is 1 and in here the input A is 1 and input B is 0. The output X should be 0. So it works here also. In here the input A is 1 and B is 1, so the output should be 1. Look here, the both A and B are 1, so the output X is 1. Here also it works true. Okay, let's move into another example using OR gate. Insert two inputs and also insert an OR gate. We have to change the number of inputs for the OR gate to be 2, and we need also one output. We have to connect the inputs with the OR gate. And also we have to connect the OR gate with the output. Okay, then let's move into our new example. Here XY are the inputs and Z is the output. So we should label the inputs as X and Y using the A button. And also we should name the output as Z here. Okay, then we move into our example. Look the truth table here. Here X and Y are the inputs and Z is the output. When X is 0 and Y 0, Z should be here X 0, Y 0 and Y is also Z is also 0. So it works here. Here input X is 0 and Y is 1. The output should be 1. Let's check this in simulator. Look here, the X is 0 and Y is 1. The output set is 1. So it works correctly. Look here, the input X is 1 and input Y is 0. The output set should be 1. Here X 1, Y 0, the output Z is 1 also. So it works correctly. Look here, the last one. When X is equal 1 and Y is equal 1, the output Z should be 1. Here also it works correct. Then we move into NOT gate. Here A is the input and B is the output. This is the input, label it as A. And this is the output, label it as B. Here I need a NOT gate to be inserted. So I click on the NOT gate and insert it between the input A and output B. Here it represents it have only one input. Then we have to connect the terminal of the NOT gate to the output and also terminal of the input to the NOT gate. Okay, then we look at the example. Here when the input A is equal to 1, the output B should be 0. Let's check it out. To check it we have to simulate that. When A is equal to 1, B is 0 here. So it works correctly. Here when A is equal to 0, B should be equal 1. Let's check it that also. Here it also correct. Here the two situations are correct. This simulation is after a lot more helpful when you have to do a very big design. Refer back to this video. Here I want to explain a simple combinational logic circuit using simulating tool logisim. As I already said, this is a simulating cursor, this is an arrow, this is text box, this is input, this is output, and these are the gates. You can also select more gates from this section also. Okay, let's look into a simple example to understand the combinational logic circuits. This is the example. This is the logic diagram of our example. This is a NAND gate, this is a NOR gate, and this is an AND gate. These are the three inputs A, B and C. This is the output Q. This is the Boolean expression and this is the truth table. Let's design our circuit using logisim and see whether it works according to this truth table of this circuit. I want three inputs here, so I click on input and put it here. Here I want to place a NAND gate, so I click on NAND gate from the gates and place here. Here I want to place an NOR gate, so I click on NOR gate and place here. In NAND gate I want a wide sized gates as gate size, so I select a wide from the gate size, and also I want number of inputs as 2. In NOR gate also I want a wide sized as gate size and also want 2 as input. I also want an AND gate and place it here. Here also I need a gate size as wide, and I also want 3 inputs to input. Here I want to put an output also, so click on output and place it here. I need to label the inputs and outputs, so I click on text box to label them and name this input as A and this input as B and this input as C, and name my output as Q. To connect the input with the gate, I want to left click on the terminal of the input and connects with the NAND gate, and also connect the AB as this to the NOR gate. Then C is directly connected to the AND gate. Then the output from the input AB from the NAND gate should be connected to the AND gate, and the output of XNOR gate having AB as input should be connected to the AND gate as this. Here the answers from the NAND gate and NOR gate and the input C are the inputs for the AND gate. For getting the output should be connected to the terminal of the AND gate as this. This is the circuit built through logisim. Then we want to check it out whether it works correctly or not when applying the truth table. See the truth table here. When C is 0, B is 0, A is 0, the output Q should be 0. Look here, A is 0, B 0, C 0, the output Q is 0. When Z0, B0 and A is equal to 1, the Q output should be 0. Look here, the A0, B0, A1, B0 and C0, the output is 0. So it correct. Look here, C0, B1 and A1, A0, then the output Q should be 0. Look here, the output is 0. So it works correctly. Here C0, B1 and A1, the output should be 0. Okay, we will check that whether it right or wrong. Here A1, B1 and C is 0, the output is 0. So it works correctly. Here C is 1, B is 0, A is 0 and the output should be Q should be 1. A 0, B 0 and C 1. Look here, the output Q is changed to 1. It also works correctly. Here C is 1, B is 0 and A is 1, the output Q should be 0. Okay, we check that also. Here A1, C1 and B0, the output is Q. So it also works correctly. When C is 1, B is 1 and A is 1, the output Q is 0. When we check it, it also works correctly. When C is 1, B is 1 and A is 1, the output Q should be 0. Let's check that also. A1, B1, C1, here the output Q is 0. This one also works correctly. So here the truth table matches with all the outputs of circuit in logisim. This is combinational logic circuits. I believe it clearly explains you how to do combinational logic circuit. Here we want to see a sequential logic gate have one bit of memory. We want to see here SR flip-flop, which is a synchronous circuit. This will explain you that how to create a SR flip-flop using NAND gates only. These are the NAND gates and this is the logic diagram. This is the truth table. Here S and R are the inputs. E is the clock. Here Q and Q bar is the output. Okay, then let's move to the logism. This is our logism window. Here I want two inputs S and R, so I click on input button and place them here, and I need two NAND gates, so I select NAND gate from the gates, and I need to place them in the logism window. This is one NAND gate and this is another NAND gate. Okay, then two NAND gates to be wanted and place here. I also need a clock, so I select clock from the wiring and place the clock between the two inputs as this. The number of inputs for the NAND gates should be turned to 2. Gate size also I need a wider one. Here also number of inputs 2 and I need a wider gate. All the NAND gates I need a wider one and the number of inputs are there 2. I need two outputs, so I click on the output button and place them in the window. The label can be used instead of using this text box to insert text. Here I want to name it as S. Look here, the name is changed as S before the input. Here I want to name it as R. The name of the clock should be E here. Okay, I need to name the outputs also as Q and Q bar. Okay, then let's move to our example. We want to connect the circuit on logism as this logic circuit. Okay, we connect the diode in there. This is our circuit. We want to connect the clock E to the circuit also. The clock E always set to be 1, so we have to simulate it to 1 always. Then we move to our example. Look here, the value of E is always 1. When S equals 0, R is equal to 0. Look here, the outputs. It indicates no change. And Q dash are outputs. Look here, the E is set to be 1. So it is initial state. Okay, let's move to the example. Look here, when S R equals 0, the comment no change. So for initial value, when S equal to 0, R equal 1, the output Q equals 0, Q dash should be 1. This is Q dash and this is Q. It also correct. Look here, when S equal 1 and R equal 0, the output Q should be 1 and Q dash should be 0. Look here, the Q is equal 1 and Q dash equal 0. So it also correct. Look here, this is R set. Look here, this is set. Okay, last one, S equal 1, R equal 1. Set S equal 1 and R is equal to 1. Look here, Q equal 1 and Q dash also equal 1. It also correct. Here the output is indeterminate or invalid. So here this R flip-flop works correctly. Here we want to see a sequential logic gate have one bit of memory. We want to see here SR flip-flop, which is a synchronous circuit. This will explain you that how to create a SR flip-flop using NAND gates only. These are the NAND gates and this is the logic diagram. This is the truth table. Here S and R are the inputs. E is the clock. Here Q and Q bar is the output. Okay, then let's move to the logism. This is our logism window. Here I want two inputs S and R, so I click on input button and place them here, and I need two NAND gates, so I select NAND gate from the gates and I need to place them in the logism window. This is one NAND gate and this is another NAND gate. Okay, then two NAND gates to be mounted and place here. I also need a clock, so I select clock from the wiring and place the clock between the two inputs as this. The number of inputs for the NAND gates should be turned to 2. Gate size also I need a wider one. Here also number of inputs 2 and I need a wider gate. All the NAND gates I need a wider one and the number of inputs are there 2. I need two outputs, so I click on the output button and place them in the window. The label can be used instead of using this text box to insert text. Here I want to name it as S. Look here, the name is changed as S before the input. Here I want to name it as R. The name of the clock should be E here. Okay, I need to name the outputs also as Q and Q bar. Okay, then let's move to our example. We want to connect the circuit on logism as this logic circuit. Okay, we connect the diode in there. This is our circuit. We want to connect the clock E to the circuit also. The clock E always set to be 1, so we have to simulate it to 1 always. Then we move to our example. Look here, the value of E is always 1. When S equals 0, R is equal to 0. Look here, the outputs. It indicates no change. And Q dash are outputs. Look here, the E is set to be 1. So it is initial state. Okay, let's move to the example. Look here, when S R equals 0, the common no change. So for initial value, when S equal to 0, R equal 1, the output Q equals 0, Q dash should be 1. This is Q dash and this is Q. It also correct. Look here, when S equal 1 and R equal 0, the output Q should be 1 and Q dash should be 0. Look here, the Q is equal 1 and Q dash equal 0. So it also correct. Look here, this is R set. Look here, this is set. Okay, last one, S equal 1, R equal 1. Set S equal 1 and R is equal to 1. Look here, Q equal 1 and Q dash also equal 1. It also correct. Here the output is indeterminate or invalid. So here this R flip-flop works correctly. Here we want to see a sequential logic gate have one bit of memory. We want to see here SR latch, which is an asynchronous circuit. This is the logic diagram of SR latch. In here S and R are the inputs and Q and Q bar are the outputs. This is the truth table of the above logic diagram. These are the initial value of S, R, Q and Q bar. Okay, then we move to logisim and create the logic diagram stated above. Here I need two inputs and place them here. I want two output also. I have to label the output as Q bar, Q dash Q and input as S and R. I want two NAND gates also. Let's arrange the logic diagram here in logisim. Then connect the output. Initially there should be 1 and R should be 0. Here Q is 0 and Q dash is 1. So it is correct. When S remains its initial value 1 and R changed to 1 from 0, the Q should be 0 and Q dash should be 1. Look here, when changing R to 1, the Q is 0 and Q bar is 1. So it's correct. When S equals 0, R equal 1 and Q equal 1, Q bar equal 0. Check that whether it's right or not. We change the value as 0 from 1. Then the output Q equal 1 and Q bar equal 0. So the output is correct. We move to the next example. S equal 1, R equal 1. Then output Q should be 1 and Q bar should be 0. Let's check it that. Here S equal 1, R equal 1, the Q equal 1 and Q dash equal 0. So it works correctly. The last one, when S equals 0, R equals 0, the output Q should be 1 and output Q bar should be 1. Let's also check them. S equals 0, R equals 0, Q is changed to 1 and Q bar also changed to 1. It also correct. We have same answer for Q and Q bar. The answer is indeterminate or invalid. Here the truth table matches with all the answers from the circuit in logisim. That it clearly explains SR latch to you. Okay, let's see how counters works in logisim. We can get counter from memory. Just select memory and click the counter in memory and drag and place them in the window. For this counter, you have to change the data bits to 4 because we want a BCD counter. Number of bits for BCD is 4. Two buttons, so click on the input or output and click on the button and drag and drop on the window. Here facing direction of the button should be changed into north. The button should be connected to the counter, so left click on the button and drag it to the counter. Then it's time to simulate the button. Click on the simulating cursor and simulate the button. If you simulate it, increase. Here you see the number is increasing. I need another button also, so select from input or output. Join the button also with the counter. I need an input to be placed here. We have to connect the input with the counter also. We have to change the direction of the input as north. Then only we can connect the input with the counter. Look here, when you press the button, the counter is increasing and simulating it. Press the button after simulating the input. Look here, the number on the counter is decreasing. Again set the value for input 0. Then press the button, the number on the counter is increasing. If you want to check the function of counter more, you can use clock or clock circuit instead of this button. I think it clearly explains you what is counter and how it works. Okay, let's move into an example for understand the encoder clearly using logism. Let's take this block diagram as example. These are the four inputs and these two are the outputs. This is input y3, y2, y1, y0 and these are the outputs a1 and a0. This is the logic diagram of the circuit. This is the boolean expression for the outputs. And this is the truth table. Okay, let's check whether the response of logic diagram in logism is correct by comparing the response with the truth table. Okay, then let's draw the logic diagram using logism. Here I need 3 inputs and also I need 2 outputs. And also I need 2 OR gates to be placed between the input and outputs. Here I need a wider gate and also I need to set the number of inputs as 2. Here also I need a wider gate and number of inputs to be set to be 2. Then I want to connect the input output with the OR gate as stated in the logic diagram. I need to name them inputs y3, y2 and y1. I need to name these outputs as A1 and A0 respectively. Okay, then we check the responses whether it works correct or wrong. y3 is equal to 0, y2 is equal to 0, y1 is equal to 0. Then a1 should be 0 and a0 should be 0. Okay, we will check it in logism. Okay, for simulating we press the simulator cursor. Look here, a1 0, a0 also 0. So it works correctly. Next, when y3 equals 0, y2 equals 0, y1 equal 1, then the output a1 should be 0 and a0 should be 1. Let's check it out. Look here, a1 0, a0 1. So it works correctly. Next, when y3 equals 0, y2 equal 1, y1 equals 0, the output a1 should be 1 and a0 should be 0. Look here, a1 1, a0 0. It also worked correctly. Look here, when y3 equal 1, y2 equal 0, y1 equal 0, a1 equal 1 and a0 should be equal 1. Look here, y3 equal 1, y2 0, y1 equal here a1 equal 1 and a0 equal 0. It also worked correct. This is the encoder circuit. It works correctly. I believe you got a better knowledge in encoder. It's easy to understand decoder when we move on through an example. This is the block diagram of the decoder. Here I have 2 inputs and 4 outputs. A1, A0 are inputs and Y0, Y1, Y2, Y3 are outputs. E is the enable. When E equal 1, one of these 4 outputs will be 1 for each combination of inputs. This is the logic diagram. In here, A1, A0 input and Y3, Y2, Y1, Y0 are output. There are 4 AND gates and these 2 are NOT gates. Normally it is called as inverters. This is the truth table of the above logic diagram. Let's build the logic diagram on logism and see whether the response are correct as truth table. We have to roll like this. Here I want 2 inputs, 4 outputs, 2 inverters, 4 AND gates and 1 enable. Then we draw that according to the logic diagram. The AND gates here should contain 3 number of inputs and I need a wider one. Draw and connect them according to the logic diagram. I want to label the inputs as A1, A0, and also I want to label the outputs as Y1, Y2, Y3 and Y0. Here I want to name outputs. So just click on output and in the selection pin I want to name first as Y3. So I type in the label section Y3. Then I want another to name as Y2, and then I want another to name as Y1, and I want the last one to be named as Y0. Then connects them according to the logic diagram. Let's check that truth table is correct or not. He always set to 1 here. when equal 1, a1 equals 0, a0 0. The output y3 should be 0, y2 0, y1 0, and y0 should be 1. Let's check it out. Look here, the y0 is 1, others are 0 when e is equal to 1. It is correct. When e equal 1, a0 equal 1, the y1 should be 1. Here only y1 is 1, other y2, y3, y0 are 0. So the response is correct. When e is equal to 1, a1 equal 1, the y2 should be 1, others should be 0 here. Look here, the only y2 is 1 here. This also true. When both a1 and a0 are equal 1, then y3 only equal 1. y2, y1, y0 should be 0. Let's check them also. Look here, only y3 is 1. Others are 0. So this one also correct. So the truth table is right. I believe that you can understood the decoders clearly using this logism. Okay, let me explain the adder using an example. This is the block diagram of our example. Here there are two inputs and two outputs. This is the logic diagram. This is the truth table of the logic diagram. In the truth table, there are A, B are input and S, C are output. This is a XOR gate and this is an AND gate. Okay, let's draw the logic diagram using logism. Okay, let's draw that logic diagram. Okay, let's move into the example and check whether the response of truth table is matches with the results of the logic diagram drawn in logism. Look here, when a equals 0, b equals 0, s should be 0 and c should be 0. Okay, we want to simulate that. Look here, s and r are 0 when a and b are 0. So the result is correct. Next one, when a equals 0, b equals 1, s should be 1 and c should be 0. Like this, s equals 1. So this result is also correct. Next one, when a equals 1, b equals 0, s should be 1 and c should be 0. Look here, s is equal to 1. This result also correct. The last one, a equal 1, b equal 1 is equal 0 and c equal 1. Let's check that. Look here, s equal 0, c equal 1. This result also right. So the whole table is correct one. I believe that you got a clear view on others. Let me explain the subtractor using an example. This is a half subtractor. This is the block diagram of our example. These are inputs. These are outputs. This is a half subtractor. This is the logic diagram and this is the truth table. Look here, A and B are inputs and D and B naught are outputs. This is a XOR gate, this is a NOT gate, this is an AND gate. Okay, let's draw the logic diagram using logism and check whether the response of truth table is matches with the results of the logic diagram drawn in logism. This is my logic diagram, which is drawn using the logism. Look at the truth table. When E equals 0, B equals 0, D should be 0 and B naught should be 0. We want to simulate it. Look here, A, B 0, D and B naught also 0. So the result is correct. Next one, when A equals 0, B equal 1, D equal 1 and B naught should be 1. Look here, A equals 0, B equal 1, D equal 1 and B naught equal 1. So this one also correct. Next one, when A equal 1, B equal 0, D equal 1 and B naught should be 0. Look here, A1, B0, D1 and B naught 0. This result also correct. The last one, when A equal 1, B equal 1 and D should be 0 and B naught should be 0. Look here, D and B naught are 0. This result also correct. I believe that you got a clear view on subvector. This is a block diagram of a multiplexer. This is the truth table. This is the logic diagram. Okay, let's see how to draw a multiplexer using logism. For obtaining multiplexer, we have to click on plexes and select the multiplexer. Then draw them according to the example. Instead of output, I like to select LED here. Here S is an enable. Normally when click on the inputs alone, the LED not work. When the S is set to be 1 and click on the I node, the LED is lights up. We can also check the multiplexer using logic diagram. So let's draw an logic diagram to illustrate that one. As stated above, okay, let's check that it works according to the truth table. When S equal 0, the I1 should be 1 and the I0 should be 0 for lighting the LED. So it is correct. Check the other one. When S equal 1, the I0 should be 1 and I1 should be 0 for lighting the LED. It also works correctly. I believe you understood multiplexer using logism. I believe that now you can clearly understand how to use logism and how to create logic circuits using logism. Thank you.